normally in ordinary everyday experience stays in this n equals 1 state. But if it can absorb energy, it can go up to a higher energy level state. We call it getting excited. And that's exactly what happens. The electron gets excited. Now, because of the way the structure of this atom exists, the electron can only exist in certain orbits. I'm not going to go into it. I keep saying this last class. It's beyond the level of the course to explain why that is the case, just accept it that it is the case. And because if you have, say, deuterium, with deuterium you would have a positive, you'd have a proton and a neutron inside the nucleus. These energy levels would be different. So although it is a heavier version of hydrogen, its spectrum would be different, okay? Because the presence of an extra neutron is going to change the structure of what's going on. And the same thing with tritium, where you have one proton and two neutrons inside the nucleus, the energy levels would be different. And then if you go to a different atom, then the energy levels are completely different. Like the ionization energy, did that dim? It did. I'm talking too much, am I?
If I press a button, will it get excited?
Oh, press the wrong button. It's brighter now, isn't it? Off the top of my head, the ionization potential for helium, the next element in the periodic table, is over 100 electron volts. I think it's like something like 110 electron volts. So it's much more difficult to strip an electron off a helium atom than it is off a hydrogen atom because of the structure of the helium atom.
And so these numbers are just for hydrogen?
Just for hydrogen. These are just for hydrogen. And we're only going to deal with hydrogen in the class. Number one, because it's the simplest element that there is, but number two, it's the most abundant element that there is in the periodic table. Okay, so we're only going to deal with hydrogen in this class. Now, the energy that you see here, this line, we could see three lines in the visible part of the spectrum. Did anybody in the class, when you looked at the lamps, did anybody pick out 4 lines for hydrogen? It's extremely difficult to pick out the 4th line. I can see it, but just because I know it's there, and sometimes I'm thinking, do I actually see it, or am I pretending that I see it? It's very, very difficult, because this is right on the limit of human visibility. 410 nanometers is a very low wavelength of light. It's not easy to pick out. Now, if you've got enough intensity, you can pick it out. If you've got a bright source, you can pick it out. That's 405 nanometers. Okay, now don't look at the purple spot. Look at the region around it. Can you see the purpliness around the really bright purple spot? The region around it is the 405 nanometers, which you might not be able to pick out easily. The problem is this is so intense that it actually causes the screen to fluoresce. And so the light that you're seeing, the really bright purple spot, is not the light that I'm interested in. It's the region around it. Probably see it a lot easier there. That's right, really, really close to the limit of human visibility. This line here is a very, very bright line, easily picked out, and it has a lovely pink color. So when we look out into space and we see massive clouds of pinkness in space, we know that they're clouds of hydrogen, because that is the most abundant color that's going to come out of hydrogen when it gets excited. And we know that it's hydrogen gas that is actually excited. And we'll show you some pictures of clouds of hydrogen in space. Now what I'm going to do is I'm going to do the calculation for the hydrogen alpha line, and then after that I want you to do the calculation for the hydrogen beta line. Alright, so let's look at what we're doing here. The equation that I gave you out last day simply states that the energy is related to the wavelength via this formula. H is a constant of nature called Planck's constant. There is the number in SI units. C is another constant of nature, the speed of light, and there is it accurately quoted in SI units as well. The wavelength is measured in meters. What I'm going to do though is I'm wanting to calculate